Okay, so one concept that is that in dynamics is the logarithmic decrement, which describes how much damping we have in the system. And the way this expression works is that it takes the amplitude, the maximum amplitude of vibration at two different points in the vibration. So one at time t and one at one period away from time t. So this is the displacement at time t, and this is the displacement at time t plus one period. So you remember this. You remember this diagram when we have amplitudes and when it repeats itself. So this, from this point to that point, we have one period. From this point to that point, we have one period, and so on. So considering the amplitude at this point divided by that point, or this point divided by that point, it will tell us how much damping there is in the system. Because the higher the decrement is, the higher the damping is in the system, and the bigger the difference will be in the amplitudes, right? So the expression that defines the logarithmic decrement is this, the ln of the displacement at time t and divided with the displacement at t plus one period, okay? And if we do this, you remember that the u, I'll show this again, the u had this expression, okay? So if we divide it with the same u at time t plus td, what will remain is this, okay, the exponential part, okay? So now to calculate the decrement, we have, as you see here, the ln of this will be this part here. Now we have inverted this because we have a minus. So the ln of this expression will be this, but without the minus, okay? And then we can also simplify. You remember that the C, which was the damping ratio, it was C divided with 2m omega, and the TD was the period, which is 1 divided by 2 pi omega. So we can rewrite this expression to get this one. So this is how we can calculate the decrement in the structure, okay? Now, if we have a structure with very low damping, very low psi, then 1 minus, if psi is for a normal, let's say a normal steel bridge, psi is say 0.005, okay, which is 0.5% damping, we say 0.5% damping. So this is 0.005 to the power of 2. This will be very little. This will be very little, and the whole thing will be about 1. So for very low damped structures, we can say that the decrement is equal to 2 pi and the damping ratio. Okay, but again, if you have, let's say that you have measured the vibrations of a building or a structure, and you have this line, you have this measured line, then you can calculate the decrement just by reading this point and that point, or this one and that one, and then going back to this relation, and you can calculate the decrement. And if you have the decrement, you can calculate the damping ratio. Or the opposite, if you have the damping ratio, and you can, based on this, you can also calculate the decrement. Okay. So the damping ratio and the decrement are two ways of the same, which tell us how much damping we have in the system. Okay. In one of the exercises of today, there is this question: how many full vibration period has the amplitude of the displacement been reduced to less than half of the initial? Okay, so how many vibration periods it take for the displacement to be reduced less than half of the initial? So to calculate this, we go back to this expression again, that the decrement relates the amplitudes is the ln of the amplitudes at time, the first time period, and the second one, which is one period away. And if we apply the exponential operator on this, this will be the exponential function of the delta is equal to this ratio. And then we can move, so we can get the amplitude at n+1, or is the same as t plus td, can be equal to this. But this can also be written as n+2, n+1, n+3, n+2, n+10, n+11, and so on. And which means that we can also rewrite this as n+2. If we want to relate this to n, then we have a 2 here. I think you can, if you don't understand this, you can just rewrite this on your paper, and you can express this again. And you'll see that you will arrive at this. So the relation is this: if it's 2 periods away, you would have a number 2. If it's 3 periods away, you will have a number 3. If it's 10 periods away, you will have number 10 here. And if it's I periods away, you will have an I here. And in the question is, so how many time it will decrease to half? Okay, this means that this will be half, because this is at certain time away, and this is at the initial, and the displacement will be half, and we want to calculate the number of cycles. So we can here calculate the I by, if we take the ln of this and then we multiply with 1 divided with the decrement, we will find the I. Okay. So this is how you should solve that exercise in today A1. All right. So what we have treated today is single degree of freedom system. But if we look around us, we will not find anything which is a single degree of freedom. It's hardly possible. But actually, many things can be simplified into a single degree of freedom system. Study, for example, this frame. Okay, this frame can be a frame in a building or a frame bridge. Okay, it's fixed to the ground, so we assume that there are no motion here. It's a fixed points. All the motion will be described in these two connections. So again, this can move horizontal, this can move vertical, and this can rotate. Same thing here. So we'll have 3 degrees of freedom and 3 degrees of freedom at this end. So in total, we'll have 6 degrees of freedom to describe the motion of this frame. But actually, we can make a lot of simplifications, because normally the walls are so stiff in the axial direction that the displacements of the wall and the motion of the wall in the axial direction is negligible. So we can say that the degree of freedom 2 and the degree of freedom 5 are actually not so important in relation to the motion of degree of freedom 1, because most of the motion will be in this direction. This is the way, for example, due to wind load, this is the way this building, this frame will behave. It will move in this direction. So we can neglect this. Another thing is that we say that the same thing this beam will not really elongate and elongate and shorten that much in relation to how much the ends of the beam will move. So we would say that the degree of freedom 4 will be as degree of freedom 1. So it will be about the same. So then we get rid of degree of freedom 4. And then we can say that the many times in, for example, if this is a frame bridge or a floor in a building, the rigidity of the floor in bending is much higher than the rigidity of the beams of the columns in bending. The columns are very rigid in the axial direction, but not in bending compared to the floor itself. So we can assume that the floor is very rigid or endlessly rigid in comparison to the walls. In that case, there will be no bending of the frame. It will just like here, as you see, it will displace like this, like a rigid body. So we can get rid of the rotational degree of freedom 2 and the rotational degree of freedom 3. And then we have converted the whole frame into a single degree of freedom, which consists of a spring. And the spring in this case will model the stiffness of the columns, not the deck. It's the stiffness of the columns that will decide this degree of freedom 1, the motion in that. And again, we will look into our handbooks, engineering handbooks, and we will find the case which looks like this, the bending case which looks like this for a force acting on the floor, giving a displacement U. This will give us a stiffness that will equal to, as you see here, for the translation, 12 EI by L3. Okay, and this is the stiffness of the spring. And then we have 2 columns, then we have a number 2 here. Okay, and then in this case, when this moves, the mass of the motion will be the mass, the complete mass of the floor, because the mass of the floor will move, plus part of the mass of the columns, the mass of the columns from here about to here that will also participate in the motion. That will be added to the mass of the system. And there we have our spring, and there we have our mass. And we have converted a frame model into a single degree of freedom system consisting of a mass and a spring. Okay. Any questions so far? Because the next that we look into is the systems that we have studied, but now we will apply also a harmonic force on the system. I will wait for a few more seconds to see if anyone will have a question, and then I will proceed. Okay. Now, so the next step, as I said, we will have a force acting and a dynamic force, P of T, acting on the system. Now, as before, we will do the free body diagram here. We will have the force in the damper related to the velocity of vibration. We will have the force in the spring related to the displacements. We have the inertial force. And then now we will have on the other side the external force P of T. And it's a harmonic, it says here, it doesn't say here, but it's a harmonic force we will study. And as you see, it will change like a sign, and it's described in this way. So it's a harmonic force that repeats itself. And sorry. So the equation of motion will be the one that we had before for the revibration, but here we will add the external force. And as you remember, we divided all the parts with M, because it from origin says mu double dot. but then we divide it with m, so we shouldn't forget to divide this also external force by m. The force was harmonic, so it can be described with a sign. And the solution of this, again, I'm not going to solve this differential equation. It's a second order linear differential equation. You can find solutions on in your mathematics books on the differential equations, and also on textbooks on dynamics. The solution of this will have two parts. One we call the complementary part, which is this one, and one we call the particular part, which is that one. Okay. Interestingly, we'll see that the complementary part is the part which is, I think you recognize the equation. This is the part that what we called before transient, that will disappear rather rapidly depending on how much damping we have. So this is the amplitude, and this is the harmonic motion. But when this disappears after a few seconds, what will remain is the particular solution, or what we also called in the beginning of the lecture, we call this steady state. So this is the steady state response, okay? So in many times, if we want to analyze a floor for dynamic loading of a machine, we will disregard the transient that will come when we start the machine, because that transient will disappear after a few seconds. We will focus our solution on the steady state part, which remains during as long as the machine is on the foundation and it's in action. Okay, so if we look at this particular solution, we would see that there is P0 divided by K. P0 is the static load. Okay, P0 is the static load, and K is the spring stiffness. And actually, this is the static displacement. This is the static displacement of the system, okay? And that part here is actually can be seen as a kind of magnification of the static response. It's a magnification factor or amplification factor or dynamic factor. It depends on what books you read. Some books call it dynamic factor, others call it magnification or amplification factor, because this amplifies the static response, okay? And it's related to the frequency in the force to the frequency of the structure, okay? So omega, as you see here, this is the frequency in the force. As you see here also, here I call it omega, capital omega, but omega is the frequency in the force. And omega n is the frequency of the structure, which was square root of K by M. But it's also related to the Xi, to the damping ratio. So if we have a high damping ratio, the magnification will be low, because if we have high here, the whole of this will be lower. If we have a low damping, this will be higher, the magnification will be higher. Another thing we see is that if the force frequency and the structure frequency are close to each other, we will end up with something close to zero here, which will magnify a lot the dynamic response. And then if these tend to be close to each other, we will have what we call resonance. We'll talk more about this also in the next lecture. Back to the diagram we saw in the beginning of the lecture. We see in blue the total response, which is this one, both the complementary and the particular together. And in red, we see the transient, which is this one. Okay, and this is the damped frequency. So this is normally not the same as a circular frequency. You saw the expression in the middle of the lecture about when we looked at the different solutions. But normally very close to the omega n. For very low damped structures, omega damped and omega n are quite close to each other, or about the same. So this is the complementary that will disappear, and what remains is the steady state, this part, that will oscillate with the same frequency as the frequency of the loading. Okay? So the oscillation here, as you see in blue, the frequency of the oscillation in blue, it's the frequency of the loading. It's not the frequency of the structure. This is something to remember. Okay, so this summarizes what we said. Also, I think sometimes you can see here, I give the pages in Chopra where you can read more about this, the dynamic amplification or the dynamic response factor. Sometimes they call it RD as the dynamic response factor or dynamic amplification factor. As this is the static displacements to the force P0, and this is the factor. Okay, so let's have a look again at our foundation. Now we have also a machine acting on it, and they want us to determine the maximum vertical displacement at point C. Okay, so 2 meters, 1.6 between the springs. We have a rotating moment. So there's a machine that rotates here, giving the rotation moment of 24 with a sign kilonewton meter. And so this is the rotating moment. Remember now, this is the equation of motion for the rotation that we derived previously for this foundation. And now we have the external moment. So this is the external moment we put here. And exactly as we did for the vertical translation, we divided with M. Now we divide with JZ, with the mass moments of inertia. We divide with the JZ. Compare these two equations. This is for the translation. This is for the rotation. They look very similar. Here we have a vertical force. Here we have a rotational moment, vertical force. We have the mass. Instead, here we have the mass moments of inertia. Angular rotation, vertical displacement. The solution should be the same. So the solution is this one for the two differential equations. Should be the same. But here, of course, we must replace the P0 divided by K. So the P0 have to be replaced with M0, and the K, remember that the K here, this is the K, should be 2KL to the power of 2 instead, okay? Otherwise, we can use exactly the same solution, but we have to remember that to replace P0 with M0, replace the K, instead of the K, we have this. Yeah, so this is basically what I already said. And we have to calculate. So it's a zero damp system. There is, as you see, there are no dampers. There are no dampers, which means that C is 0, C is 0, and C is 0, which simplifies this equation. This means that all of this will disappear. And we will end up, and we will neglect this one because we are analyzing the steady state response. So what remains is actually this part here. This part will remain. Okay. So this part, if we're interested in plotting the complete harmonic motion of the slab. Or if you're only interested in the maximum will occur when all of this sign is equal to 1. This is the maximum displacement. And we said that P0 by K can be replaced with this. And then we just calculate the ratio of the forcing rotational frequency with the rotational frequency of the structure. This was 14, as you remember. We calculate this in a previous slide. It is 14 hertz. So in radians per second, omega, we have to take the F multiplied with 2 pi. And this is for the machine was given. And we get this angular displacement, which is in radians. Okay, and then what they ask in the example 3 is the maximum vertical displacement. So this is the angle. We have to multiply this with the distance to point C, and the distance was 1 meter from the center of gravity, and then this will give us a total displacement, the maximum total displacement of 42 millimeters. Okay. And as you see, this is quite a lot. So 4 centimeters, if you have a machine on a floor and the floor is standing on pile foundations of this kind, and you have a displacements of 4 centimeters, that will never be allowed. Not only because human beings working on this floor will feel the vibrations and will be scared, but this will also jeopardize the function of the machinery. Okay, so many machines, when you purchase a machine in a factory, they will tell you, and the manufacturer of this machine will tell you what is the maximum level of vibrations that is allowed, and it's normally a millimeter, in a millimeter level or less than that, depending on the type of the machine. If it's an X-ray machine in a hospital, then the level of vibration will be in an order of decimals of a millimeter. So 4 centimeters is very high. And the reason that 4 centimeters, that this is as high as 4 centimeters, is actually because, as you see here, we are very close to resonance. You see here that the external force have a rotational frequency of 30, and the floor itself has a rotational frequency of 40 multiplied with 2. So this is the omegas. Okay, so they are extremely close to each other. If we put 30 here, then this will probably increase more than double. Okay, and such rotations will of course break the piles, and it will crack the foundation as well. So that's a problem, obvious problem of resonance in this case. If we want to increase, if we want to decrease the level of vibrations, what can we do? We have actually 3 alternatives. So one alternative is, of course, to increase or decrease the stiffness of the foundations. So we can go back to this foundation and we can decrease the K. If we decrease the K, we will end up with a frequency much less than 14, which will be quite away from the 30, and then we will have not resonance. But the problem is that if we decrease the foundation stiffness, the static displacement will increase, right? So then just by putting some loading on the foundation, it will displace in a static manner quite a lot. So it's not a good way. We can increase the stiffness of the foundations By increasing that, we will increase this also. So we will end up with a frequency of the foundation which is higher than 30. And then by doing this, we will decrease the displacements. One problem though is that this will be quite expensive, because then we will have to put a lot of more piles. We can change the mass of the foundation by increasing or decreasing the mass of foundation. Then we will change also, remember that by doing that, we will change the J. Where do we have the J? Because the J is the mass multiplied with the perpendicular distance divided by 3. So that's also one way, by playing with the mass. Another effective, if this foundation is already built and we cannot adjust the mass of the foundation and we cannot add more piles to foundation, would be very expensive and very difficult. What we can do is that we can increase the damping of the foundation by putting dampers. What we will do, we will add damping to the foundation. For example, under the if the machine will be applied here, under the machine we will put dampers, isolators and dampers. Then what we will do is that we will increase the Xi. The Xi in this case was 0 here because we had 0 damping. But if we increase damping, we will increase this part here. By increasing this part, we will decrease the magnification factor. So even though these are close to each other, 14 multiplied with 2 is close to 30, but we will have another term here with the damping that will also be very efficient way of decreasing the whole thing and lowering the amplitude. Okay, so that's a little bit about this example. There is also something, I have 10 minutes, so I'll have to hurry up a little bit. There is something that is called phase lag, which is a very important concept that you will have to understand. You will also see it in the lab 1. It can be calculated like this. Here again, you have the Xi, you have the ratio of the forcing and the structure frequencies. And this is actually the delay. This can be seen as the delay between the displacement of the force and the displacement of the structure. It's not always that when the force has its maximum, the structure has its maximum displacements. There can be a delay. The maximum displacement can come before or after the maximum of the force. And this delay can be calculated as the phase lag, okay? Very important concept. Just before finishing, I have about 10 minutes. I will solve this. Normally I solve this on the board, but now I have included the solution here on the slides. So this is a simple mass connected to the dashpot C and to the spring stiffness K. And I see there is a question here. I can take the question after I go quickly through this example. And so there is a mass of 100 kilograms connected to a spring with a stiffness of 30 kilonewton per meter and a damper with 1,000 Newton second per meter. And there is a force acting here with the magnitude F0 is 80 Newton and omega is 3 Hertz multiplied with 2 pi. So the frequency F is 3 Hertz. And calculate the steady state amplitude of the displacement of vibration in part A, and calculate the phase between the force and between the displacement. Okay, so first calculate the amplitude. Okay, so the mass, 100, K, the C, everything is given. So we can calculate the omega n just by the square root of K by M, stiffness in Newton, the mass in kilograms. It will give us 17 radians per second. So that's the structural frequency. The frequency of the force was given. It's 3 Hertz. So we see that the ratio between these two is 1.088, close to resonance. We can calculate the damping, critical damping, as you see from the expression previously, it's 2m omega n. So 2m omega n. And C was given 1000. It's 0.29. It's very high. I can tell you that this is 0.29, which is 29% of the critical, which means that this is something equivalent to damping we have in automobiles and in these kind of structures, quite high damping. In bridges, we have maybe 2, so 0.02 instead of 0.2. And then the dynamic factor, the magnification factor, can be calculated as this. In the steady state response, we just put the numbers and we get 1.52. So this means that the static displacement, this is the static displacement, F0 is the force, which is 80 Newton, divided with the K. This is a static displacement, and this is the magnification. This will lead to 4 millimeters. So the static displacements are magnified by 50%, 52%, but still they are very low because of the high damping, 29% damping, 29% damping. Okay, so the next is to calculate the phase angle. And you saw this equation for the phase angle. Again, we have all what we need. So just a matter of entering and calculating this. It will be 1.8 radians or 106 degrees. So what does this mean? As I said, this is the angle between the delay. You can see it as the delay between the force and between the displacement. So you can plot it. I'm not good in plotting things like this, but I tried to do it this morning. And if you see this, let's say that the displacement is here, okay? So for example, at time 0, this is oscillating at time 0, the displacement is here. The force doesn't have a 0. The force is 106 degrees away. So, but when the force gets 0, the displacement will be probably at maximum. So there is a delay between the force and the displacement. Okay, so this is the way you can imagine the results. Okay, so this was the last slide for the lecture. I'm sorry that part of it was a little bit maybe unclear. This is a challenge, I think, for most of us. This is actually the first time I